So this afternoon, we'll be talking about gamma distribution. But this time, what are we looking at? Well, first of all, look at the moment generated function. Then we look for the mean of that distribution. Then we also look for the variance of the distribution. But first of all, let's look at the probability density function of gamma distribution, which is given as I said f of x equals to say lambda raised to power alpha. So x, so x raised to power alpha minus 1. Then we have an exponential raised to power minus lambda x, all divided by however alpha here. So in the case whereby x is less than positive infinity but greater than 0. So we have the function this way. Now the moment generated function, we said m of x of t equals to expected of exponential raised to power tx. So now looking for the moment generated function of this gamma distribution, then we say we're going to have m sub x of t will be equals to integral from positive infinity to 0. Then we have an exponential raised to power tx. Then we have f of x dx. In the case whereby our f of x is this distribution up here, so now we're going to have this is equals to is 0 runs to positive infinity exponential raised to power tx. Then we have this now, we say lambda raised to power alpha x raised to power alpha minus 1. Then we have exponential raised to power minus lambda x, all divided by, you have the alpha here, so everything the x, so which means we are integrating with respect to theta x. So now what do we do now? We see that we have an exponential here, we have also a half exponential here, so we can join these two exponential together. We're going to have the same integral is 0, so positive infinity, then we have exponential. So if we factorize, we have a minus x into brackets, so it will remain lambda here. So since we factorize minus here, this is also going to be minus t. Then we have a lambda raised to power alpha x raised to power alpha minus 1, then all divided by alpha. Then we have a delta x. We've seen this now. Now there is a way whereby we can manipulate this function here so that it will be easier for us to get our moment generating function of that distribution. And what do we do right here? So since we have a alpha minus, so we have lambda minus t here, so we can just factorize that. Now if you look at this, now we are differentiating this with respect to x. Now if you look at this lambda raised to power alpha, it has nothing to do with x, so we can take it out. We say we have a lambda raised to power alpha. Now we'll manipulate this, say divided by, we'll bring something of this nature to the denominator here. We have a lambda minus t raised to power alpha. Can we see that? Lambda minus t raised to power alpha. Then we continue. Integral 0 to positive infinity. So exactly what we put at the denominator, we're going to put it here now. We have lambda minus t all raised to power alpha. So by the time we divide this and divide this now, so we have 1. It means we've done nothing in this place. Now since we now have lambda minus t alpha, then we'll continue with what we have here. Saying x raised to power alpha minus 1. Then we have the exponential function, which is exponential raised to power minus x into brackets lambda minus t. So we still have all delta x, and we should not forget this denominator. We have everything divided by, so we have the sign alpha. So what should we do now? We should also note, so if you look at this now, we have here, instead of lambda, so we have it as lambda minus t. Now instead of lambda, we have it as lambda minus t. So which means we are not dealing with ordinary lambda now, we are dealing with lambda minus t. So it means all this now is a sample point. We said if you have this now, know that. So know that if you have this, which is a integral is 0 to positive infinity, you have f of x, the x, all will be equals to 1 because this is the probability of all sample space. Now, therefore, all this value here, everything here is the probability of all sample point, which is going to be 1. So we say integral alpha runs to 0, then we have a lambda minus t all raised to power alpha, x raised to power alpha minus 1, then exponential raised to power minus x into bracket lambda minus t, then divided by this delta x, all will be equals to 1. All will be equals to 1. Now, since all of these are equals to 1, going by this, so we're going to have a this equals to, we say lambda raised to power alpha divided by lambda minus t raised to power alpha times 1. And by the time we multiply this by 1, we're going to have a m subscript x of t, which is the moment generating function, to be equals to, say, lambda raised to power alpha divided by lambda minus t or raised to power alpha. So this is the moment generating function of gamma distribution. Now we are through with this. So from this moment generating function now, it will be easier for us to find the mean. It will be easier for us to find the mean. And how do we find the mean? That is the first derivative of moment generating function. The first derivative of moment generating function when t equals to 0 will give us the mean. So we say the mean of this distribution will be equals to, say, m prime x of 0. That is, when we differentiate this first difference of this moment generated function when our t equals to 0 will give us the mean. So what do we do now? So before we start differentiating, we can write this, the moment generated function, say mx of t to be equals to, we can write it this way, saying lambda raised to power alpha into bracket lambda minus t raised to power minus alpha. We can take it up so that it will be easier for us to differentiate. We can use a quotient rule to differentiate this, but now that we put it this way, we can easily use our product rule. So we're now saying m prime x of t will be equals to, so what do we do now? If we differentiate this now, we are going to have, if we keep this and differentiate the whole of this now, already keep this now, we have lambda raised to power alpha, then we should not forget that we're going to use this to multiply this. So we have into bracket minus alpha, then bracket open, we can now have the same lambda minus t raised to power minus lambda minus alpha minus 1. And we should not forget that when we differentiate this inner value here, we are differentiating this now. If we differentiate with t now, we're going to have minus 1. We're going to have minus 1. So we have all multiplied by minus 1. So we can use this is a function of a function, and we have a product rule. So for us to know that, we should know how to differentiate this using function of a function. So multiplying all this together, this minus, and we should not forget that since we're having minus here, this minus will neutralize this minus. So we're going to have alpha lambda raised to power alpha, then we have into bracket lambda minus t raised to power minus lambda minus 1. So we can easily find what we need now. So now we just say when t equals to 0, so we need a m prime of x when t equals to 0. So this will lead us to have a alpha lambda raised to power alpha, then into bracket lambda minus 0 minus lambda minus 1. So this is what we are going to have here now. You can see alpha lambda raised to power alpha, then we have the lambda minus 0. So now from this point, when we have this as 0 now, we are only going to have a lambda here inside the bracket. Now let's move. So from this point here now, which is this, we're now going to have, we say we have m prime x of 0 equals to, we can see I continue from here. This is the previous page. So we have a m prime of x equals to what we have here, which is a lambda alpha lambda raised to power alpha, then we have into bracket lambda raised to power minus alpha minus 1. So the all of this is going to be since this is 0, so that is what we're going to have here. So from that point now, so from this point now, we can easily have this and say we have a m prime x of 0. So since we already have this now, so what can we do here now? We can factorize this or this negative here now. We have this equals to alpha lambda raised to power alpha, then instead of we have into brackets lambda minus into bracket, so we can have it as alpha plus 1. Can see that we have alpha plus 1. So therefore we easily have gotten what we need here, and we can also write this way. We say this is equals to we say alpha lambda raised to power alpha divided by, since we are bringing this down, we are going to have a lambda raised to power alpha plus 1. We have alpha plus 1. So since we have this to be of this nature now, saying alpha plus 1, we can easily write this format, and we're going to have, let me separate this into 2. Yep. So we can write this easily and say alpha lambda alpha, then we have lambda raised to power alpha divided by, so we can split this into 2, which is going to give us lambda raised to power alpha multiplied by lambda. So this alpha lambda and this alpha lambda is going to cancel each other. So what we left now is alpha raised to power lambda. So therefore our e of x, that is the mean of gamma distribution, which is mx of 0, will be equals to what? We have alpha divided by lambda. So this is the mean of gamma distribution. So now we need to find the variance. And for us to get the variance, we should remember that variance of x will be equals to e of x. We can say e of x squared minus e of x, now say e of x all square. So we can have it that way, say e of x square minus e of x all square. And this e of x is what we've gotten here. Now we need e of x raised to power 2. That is the expected square value of x. And how do we get this? And for us to be able to get e of x, we say e of x squared. That means we need the second derivative of the moment generator function, which is m prime prime. So we say we have a m prime prime subscript x of 0. That is what will give us what is it called? It will give us the expected square of this gamma distribution. So how do we do this now? So we are going to differentiate this what do you see here? Ms of t, that is from this level now, we're going to differentiate that. Let me write it. That is m prime, that is the first derivative. M prime of x of t equals to alpha lambda raised to power alpha into brackets lambda minus t raised to power minus alpha minus 1. So that is what our m prime prime, that is what our m prime give us, which is the first derivative. So we need the second derivative now. That's what I want to do now. So all right, alpha lambda square, this is what we want to differentiate now. This is a product rule, and this other function is a function of a function on its own. So we keep this since we have to know how to differentiate, or we know how to use product rule and composite function. So we are going to keep this and differentiate the other function here. And if we do that, we're going to have a, we are keeping this now. So we are going to have a m prime prime x of t, that's the second derivative. And here we're going to have say alpha lambda raised to power alpha, that is, we're going to keep this, then multiply by the derivative of this composite function. If we differentiate this, we're going to have a alpha plus 1, then into bracket we say lambda minus t raised to power minus alpha minus 2. We are going to subtract 1 here. Then we have a plus. Now we are going to differentiate this now and keep this. So by the time, we are going to keep the whole of this, and the other time we keep this, we differentiate this. Now this time around, we gonna keep this and differentiate this. And if you do that, we're keeping this, so we have a lambda minus t raised to power minus alpha minus 1 multiply by, so if you differentiate this, it has nothing to do with t, so the whole of this is going to be 0. So it means the whole of the other part here is going to be 0, and as such we're going to have our m prime prime x of t to be equals to we have alpha lambda raised to power alpha, then into bracket we have alpha plus 1 bracket close into bracket lambda minus t raised to power minus alpha minus 2. So that is what we have left. So from this point now, what do? We can now make our t to be equals to 0. So in that way, that is the only way we are going to have our m prime prime. So we say m prime prime x of 0 now will be equals to, that is, anywhere we find t here, we're going to substitute it with 0. And what do we have? So we have this is alpha lambda raised to power alpha, then alpha lambda raised to power alpha into bracket alpha plus 1 into bracket we have lambda minus t, and we should not forget that our t equals to 0, so this is going to be minus 0 bracket close, then we have a minus alpha minus 2. So therefore we can have this as a, say, alpha lambda raised to power alpha into bracket alpha plus 1 into bracket lambda raised to power minus lambda raised to power, we have minus lambda, minus alpha minus 2. So this is what will be left. And we can also factorize negative here, and this is going to give us alpha lambda raised to power alpha into bracket alpha plus 1 then into bracket can have this lambda, then we say minus into bracket alpha minus 2. So in a real sense now, this is our m prime prime x of 0. Say m prime prime x subscript x when t equals to 0. And we should not forget that this particular one, we can write this, we say alpha lambda raised to power alpha into bracket alpha plus 1, then divided by what we have here, which is lambda raised to power alpha then minus 2. And we should not forget that when we factorize this is going to be positive. I made a mistake here. This is going to be positive. So we have plus 2 since we'll take it back to the denominator side, and we can split it down and have it this way. What do I mean by that? We can have it as saying d is equals to alpha lambda raised to power alpha into bracket alpha plus 1 divided by alpha raised to power lambda, then we say multiply by lambda raised to power 2. So we have lambda raised to power alpha multiplied by lambda raised to power 2 using the law of indices. Therefore, lambda raised to power alpha will cancel this lambda raised to power alpha. So what do we have left here? We are going to have a alpha into bracket alpha plus 1 divided by lambda raised to power 2. So if we open this bracket now, finally, we're going to have a, what is it called? We're going to have a alpha square plus alpha divided by lambda raised to power of 2. And this is our e of x square, which is equals to m prime prime of x when t is equals to 0. So now we now go back finally to our variance. We said variance is equals to, we remind us, we've already wrote it here already. We said this is e of x square, and e of x square, which is equivalent to m prime prime x of 0 equals to this. So we're saying we have a alpha square plus alpha divided by lambda raised to power 2. Then we have it a minus e of x square. And what do we have here? We have all this. And when we square this, we're going to have an alpha square divided by lambda square. So we can see we have variance will be equals to, since we have same denominator, and this alpha square will definitely cancel this alpha square. So what we have left now is going to be alpha divided by lambda raised to power 2. So this is the variance of gamma distribution. And what we mean by, you have lambda square, lambda square. When we take the LCM, this alpha square will cancel this alpha square. So what remains here is alpha. So this is the alpha. Then we have the LCM, which is lambda square. So this is how to find the moment generator function, mean and variance of gamma distribution.